Yeah, welcome to Massive Open Online course on chemical process intensification. So, we are discussing about process intensification in extraction under module 10, and in this module today we will discuss more about the process intensification in extraction, and in this lecture we will discuss supercritical extraction for process intensification. Now, you know that the intensification of the separation technologies with fluids at high pressure are essentially vital to get new natural products in greenery way, and also with that more efficient way, and also that whatever products is coming based on this intensification of supercritical extraction, we can have the products of free of residual solvent, and that typically present high quality when compared to products that obtained by conventional techniques. And the extracts of that bioactive compounds can be obtained by extraction of solid matrix, leaves, seeds, pulps, etc., or by extraction or fractionation of liquid mixtures, aqueous solutions, fish oils, microalgae oils, vegetable oil, deodorized distillates, etc. Also at high pressures we are near or above the critical point. The solvent density increases drastically at these supercritical conditions, and this is the most important parameter associated to the solvent for extraction. In the previous lecture we have already discussed the basics of extraction process as well as various aspects of intensification. So, we are not going to discuss again here that basic principles of the extraction, only we will discuss about that supercritical extraction by solvent of that supercritically conditions. Now, what is that supercritical extraction? Now, as per definition we can say that the separation of one component, the extractant from another, the matrix using supercritical fluids as the extracting solvent. It is a diffusion based process actually, in which the solvent is required to diffuse into the matrix and the extracted material to diffuse out of the matrix into the solvent. And the diffusivities are much faster in supercritical fluids than in liquids, and also because of that this extraction based on these supercritical conditions will be faster. So, basically this is a diffusion based process. How you can intensify the diffusion so that you can get more extraction in this particular high pressure systems. Now, very important point here that what are the solvents that you can use for that extraction process under the supercritical conditions. Now, carbon dioxide that at its supercritical conditions will be acting as a solvent which will be non-toxic in properties, and also it will be acting as solvent, co-solvent or anti-solvent also. And it is the most important fluid used in the supercritical fluid technology in extraction, even that separation, fractionation, microionization and encapsulation process. And it is actually applied to obtain extracts that is constructed with bioactive compounds for food, pharmaceuticals and also cosmetic applications. Now, here see that we can say that this is the carbon dioxide can be acted as a co-solvent, even solvent, anti-solvent, and from use of this carbon dioxide as a solvent you can produce that natural matrix, and where through which that this you can separate the solutes by this carbon dioxide solvent. And in that case whenever passing through that natural matrix, it will go to the extraction process at high pressure, and also after that at this high pressure that through this natural matrix this separation of the solids will be there, and whatever compounds will be coming, that will be called as bioactive compounds at its higher operating conditions of pressure and temperature. Now, if you say that carbon dioxide of course has a critical temperature near to room temperature, but here pressure will be a little bit higher, in that case contributing to the operating conditions to extract thermolabile substances, and also you can say that it will be as in bioactive compounds. And also this carbon dioxide acts as a co-solvent when in the mixer it will be used more than 60% of ethanol or water, and also it can be used as an anti-solvent when the solute extract is not soluble in carbon dioxide during the depressurizing step. And it is a non-polar, and also to enlarge the application spectrum to extract bioactive compounds, ethanol, water or both are usually used as co-solvents there. So, this is the actually condition at which you can get that supercritical solvent of carbon dioxide. In this case, the thermodynamic phase equilibrium that will determine the limits for the mass transfer among different phases. Here in these slides, we are showing that different phase equilibrium condition of ethanol, carbon dioxide and water. Whereas ethanol, you will see that here at this diagram, here P versus temperature, that means here this is the critical condition at which that this ethanol can be actually a liquid as well as vapor, and also above that it will be a solid, and sometimes above this critical condition it will be considered as a a supercritical fluid. So, as an ethanol, you can say that at 61.48 pressure and also that temperature of 514 Kelvin, it will be the point of condition, or you can say that the condition of pressure and temperature which is representing the critical point of this ethanol. And you will see that if you increase the pressure from its triple point at here, and if you increase the pressure and also increase the temperature, you will see that how the equilibrium conditions are there, and when this ethanol will be remaining as liquid, and where and at which condition it will be as a vapor there. And also above this that triple point, you will see that there will be a that some equilibrium condition of fusion, where that solid may be converted to liquid or liquid may be converted to solids there at this equilibrium pressure and temperature. Whereas similarly that carbon dioxide is little bit higher that pressure, and also the temperature is also at lower relative to that ethanol for getting that the supercritical condition. And here also you will see that triple point will be that different from this ethanol. So, this is the gas will be actually converting to the solid, liquid, and also supercritical fluid at different operating that condition of thermodynamic condition of pressure and temperature. So, above this critical point you have to remember this, when this carbon dioxide gas get the supercritical condition beyond of this pressure and also temperature. And water also you will see that this is the triple point, where that gas, liquid, solid will be at this point will be same in that case, and beyond these points this is the liquid condition, and this is the vapor, and this is the solid conditions. And the supercritical condition, that is critical pressure, will be as that 221 bar, whereas this critical temperature will be that 647.15 Kelvin. So, beyond this pressure and temperature, the water will be acting as that supercritical condition. So, these figures actually show the pressure temperature diagrams for the carbon dioxide, ethanol and water, and the substances most commonly employed as the co-solvent ethanol and water in high pressure extraction processes of bioactive compounds. And also you will see that you have to remember the triple point of carbon dioxide is of pressure of 5.18 bar and at a temperature of 216.58 Kelvin, it is around 56.57 degrees centigrade, that is a negative, and the critical point is at pressure of 73.7 bar and temperature of 304.14 Kelvin. So, this is the condition at which you can get the that transition of this supercritical to the critical and then triple point condition, and also the changes of phase from liquid to solid, solid to liquid, or liquid to vapor and vapor to liquid, like this. So, when the substance is in the state above the critical temperature and the critical pressure, it is called the supercritical fluid. Now, why that that this carbon dioxide to be actually acting as intensified extraction process as a solvent at this supercritical condition, because that you will see that at this supercritical condition the properties of that carbon dioxide or other that fluids will be changing. In that case, density is the most important thermodynamic property to define the solving power of a solvent at high pressure, because in that case the solvating power of the solvent will be changing at this supercritical condition. Now, increase the density of the solvent increases its solvating power at the supercritical condition. And in the figure you will see the dotted line here shown that within the saturation curve is the two phase region. In saturation curve there is a this is called saturation curve, and there is a certain difference in the density between the liquid and the vapor there at a different temperature. So, at a different temperature, if you increase the that pressure, you will see that density accordingly will be changing at a different temperature. So, for carbon dioxide you will see that critical point is at the pressure of 73.7 bar, and at the temperature of that 304.1 K. In this case, it makes carbon dioxide the most applied solvent to extract the thermosensitive materials. So, density is one of the important thermodynamic property to define the solvating power of the solvent for the extraction process at this high pressure. Now, what are the general process step of the supercritical fluid extraction? Generally, the supercritical fluid extraction applied to a natural solid matrix that consists of three steps, like the system supply of solvent or co-solvent, the extraction unit, and the extract separation system from solvent or co-solvent. And this is the general schematic diagram for the supercritical fluid extraction unit. You will see this is the extractor here, and in this extractor the carbon dioxide will come after compressing as a supercritical condition, and this supercritical condition, this carbon dioxide gas go to the extractor, and then from that extractor this supercritical carbon dioxide with extractant it will come, and after that it will pass through the separator, where that extractant will be separated from that carbon dioxide, and that carbon dioxide will again will be that condensed, and it will get as a liquid carbon dioxide, and after that it will be pumping and compressed, and at its supercritical condition again it is to be sent to the extractor for the extraction of the solute. So, this is the basic that schematic diagram of that supercritical extraction unit by using that solvent of carbon dioxide. Now, the supercritical solvent continuously flows through a fixed bed of the solid particles and dissolves the extractable components of the solid, and the solvent is then feed into the extractor and evenly that distributed at the inlet of the fixed bed, and the system solvent and the soluble components leave the extractor and feed the precipitator or separator, where solvent products are separated by expansion. So, this is called depressurizing condition, and you will see that at low pressures the density of the solvent of course will be decreases sharply, and because of that it decreases the solubilizing power of the solvent as well, and also the product's precipitation. So, based on this, you know that changing of density with respect to pressure, that changing of that solubilizing power, that is tends to decrease, and also that because of that there will be a precipitation of the products, and based on which that that separation will be there. Now, choice of operating condition, how you will choice that operating conditions for that particular extraction process, and in this case the choice of the operating condition actually mainly a factor that contributes to the maximization of the extract solubility in the supercritical solvent, and also it will give that consequently the extraction yields. If you increase the density, you will see that supercritical fluid, its solubility of the solvent will be maximized, and in that case the solubility increasing can also occur when a co-solvent is added, which changes the solvent power, and this way the new solvent is a mixer, it will act and it will enhance that that separation efficiency. And how to design of those that extraction column, in this case to design a high pressure fluid extraction process of valuable compounds from new natural solid matrix, it is of course necessary to define the size of the extraction unit and some important parameters that is to be determined to obtain the optimum process condition for each application. So, you have to define the system in such a way that size of the extraction unit should be minimized, and also parameters like mass transfer, even solubility criteria, even packing materials, and also if what is the channels and also flooding conditions is there or not. So, everything should be that considered for the optimization of this design unit there. And most important design parameters for this extraction process actually are the operating conditions, that is pressure and temperature, and amount of solvent, conditions of solvent that will be removed from the extractant, and also the pretreatment of the solid matrix and other mass transfer parameters. So, these are to be actually considered as a design parameters. Now, what are the actually different variables that affect on the mass transfer behavior in this supercritical extraction process, because that ultimately the pressure and temperature is the one important factor for this mass transfer process, and since you are going to increase that mass transfer phenomena based on that pressure and temperature, but there are some other hydrodynamic characteristics also you have to think about, because that solvent whatever you are actually allowed to pass through that packing materials of that extraction device, that how actually that solvent will be distributing inside the bed. That distribution parameter also important to actually enhance that mass transfer process, that is called that extraction process. And also that configuration of the bed also, that is important. Sometimes that the packing materials will be the staggered, sometimes that packing material the stage wise, sometimes that packing material may be at that certain structured. So, that also can be considered to affect on that mass transfer behavior, and also based on that study you can also assess that whether that intensification of the process is possible or not. And also particle size is also important, because based on that particle size you will see that mass transfer will be happen over the surface of the particles, and it may enhance the contact between that solvent and the solutes, and also liquid and liquid there inside the bed by that well distribution by these packing materials. So, particle size sometimes it will be that a factor for that mass transfer behavior. And height and diameter, of course, very important, that if you increase the height and diameter accordingly, that that you will see that mass transfer phenomena will be there, because all these mass transfer coefficient, we know that depends on that mainly 3 or 4 types of variables, like one is called dynamic variables, that is flow rate of the fluid and distribution of the fluid, and then you can say that geometrical variables, where you can consider that particle size, even that channeling, or that special configuration of the bed, and height and diameter. And also another important factors is that what type of solvent you are using. If you use different solvents, like those have different physical properties, accordingly at supercritical condition, those physical properties will be changing at its supercritical condition. So, those affect, those physical property change also, it may affect on that mass transfer characteristics. And also that this mass transfer behavior will change also if the materials or solids are getting the precipitated or not at its supercritical conditions during the extraction process or not. That is very important, because that depends on that how that solubility will be assessed there, and also solvation power of the solids there. And then of course, that solvent flow, that is one dynamic variables. Another important variable, that is called thermodynamic variables. Of course, this is pressure and temperature. So, these are the variables, like that dynamic variables, geometric variables, physical properties as variables, and the that thermodynamic variable. These 4 types of variables are mainly important for changing of this mass transfer behavior. Now, what is that high pressure carbon dioxide properties that actually affect on that mass transfer characteristics of this supercritical extraction. In this case, viscosity is one of the important factor, and it is actually decreasing with that high pressure, and also that diffusivity is also increased by that decreasing that pressure, and also you can say that the viscosity is decreasing with decreasing the pressure, and thermal conductivity that is that increases with that temperature, but pressure is decreasing in that case. And dielectric constant also is one of the important physical properties at this supercritical conditions. So, at this dielectric constant, this will give you that carbon dioxide is polar or non-polar, and then carbon dioxide a polar, and then it will be acting as a carbon dioxide as a solvent, and then that it will be used as a supercritical extraction by considering it as a solvent. Now, let us consider some applications of this supercritical extraction, like if you want to extract that some essential oil. So, in that case, isolating essential oils, the use of carbon dioxide as supercritical fluid is generally considered as a chemically green solvent, and it is unconventional extraction techniques that does not alter or degrade the substances present in oils, because it uses relatively low temperature in the extraction process. So, carbon dioxide as a solvent at its supercritical condition will be acting as a that green solvent, which is more that intensification for this extraction process. And another application is called phytoesterols extraction. In this case, the plant sterols, that is called phytosterols, are non-volatile terpenes. In that case, the great majority of these compounds are formed by carbon with 1 or 2 carbon-carbon double bonds, according to Mauricu et al. In 2002. And these compounds have various biological activities, such as lowering the total serum or plasma cholesterol leaves and the low density lipoprotein and cholesterol labels, and also they have anti-tumor activities, inhibiting capacity and also the development of colon cancer by that is anti-tumor activities inhibiting that development of colon cancer, and that is why this phytosterols is very important, which is to be extracted by the supercritical extraction in efficient way and also green process. And for the extraction of these phytosterols, the supercritical carbon dioxide has been shown to be the efficient technique for extraction of the fixed oils from these vegetable matrix. Another important materials, it is called carotenoid extraction. It is very useful compounds present in plants that have several applications in food, cosmetic and pharmaceutical areas. In this case, this supercritical extraction process is used to extract this compound, and it is very beneficial in a short time in relation to the conventional process. And also in this case, it is not required to use some toxic solvents to collect those compounds of interest, as reported by Melau et al. In 2016. So, supercritical extraction is the greenery process of extraction by which you can extract this carotenoid extraction, carotenoid substance without using that some other toxic solvent. Now, fatty acid extraction, you will see that fatty acids generally that belong to the lipid class and differ according to the size of the carbon chain, which is in range of 2 to 80, and the presence or absence of double bonds or their radical functions as the groups hydroxyl, epoxy and halogen atoms. In this case, that this fatty acids extraction by that conventional solvents is not so easy, and it is time consuming, as well as that more energy consumptions, more it is not also economic, and it is not the eco friendly. So, that is why extraction by the supercritical fluids or high pressure carbon dioxide is significantly used as a better techniques to get better yields and performance compared to the other conventional processes. And in that case, it is actually also giving that high performance of the mass transfer during that extraction process to get these fatty acids without using some other toxic solvents. So, Kauba et al. 2016 they have reported that canola seed dehulling on the oil recovery by cold processing and supercritical carbon dioxide extraction, that this type of extraction even in fatty acid extraction it is very that useful. So, that is why process intensification by the supercritical extraction is coming based on this greenery development or sustainable development, or by green synthesis you can say. Extraction with supercritical carbon dioxide modified with ethanol or water mixture. In that case, the extraction with supercritical carbon dioxide modified with water in different proportions, that is carried out to obtain bioactive compounds of high polarity, because this carbon dioxide is a non-polar molecule, and also it does not have power to stabilize polar substances, as is the case of the phenolic compounds. So, phenolic acids and flavonoids, there is that phenolic compounds, and in this case this carbon dioxide as a supercritical solvent, we can say that we are or you can use to get more yield of this that extraction with this ethanol or water. And in that case, mainly it depends on that the yield of this substances at the end of the extraction process. Mainly depends on that solvent flow rate, percentage of co-solvent what you are using, even co-solvent type, whether it is ethanol or water, even also that extraction time. So, these are the factors which actually to be considered during this extraction of this supercritical carbon dioxide with ethanol or water. Now, we are talking about that supercritical extraction, but what about the subcritical extraction? What is the comparison of the supercritical extraction compared to that subcritical extraction? Now, supercritical extraction, you will see that is a much stronger solvent than subcritical carbon dioxide, which will allow for a faster and more complete extractions there. And by supercritical methods, the lighter oils as well as the that not so describable higher molecular weight materials like waxes, paraffins, lipids and resins can be extracted there. And these fatty waxes etc., will then need to be removed from the extract by a process that is called winterization. And the advantage of that subcritical over supercritical is that the extracted oil is pure, free of fat, waxes and lipids. So, less post processing work if any is required, and in that case the purer oil does not need to be further refined and can be used just as it is, edible and other products there. Winterization, in that case after getting that products after that supercritical extraction, you have to again separate those extracted materials there by winterization, and based on this winterization method the extract is mixed well with some alcohol and then put in a deep freezer overnight, and after that the mixture is poured into a funnel through a filter paper, trapping the waxes and lipids. And then this process can be done several times to completely filter all the unwanted materials. Once the oil is filtered, the alcohol is then removed by heating the oil extract using a rotary evaporator or some by other means. And so, we have discussed that different aspects of carbon dioxide extraction at its supercritical conditions in a greenery way, so that we can get more yield, more performance, even intensification of the extraction process based on this. And also some processes may be the more advantageous in subcritical conditions, but some the materials which will be more more favorable at its supercritical conditions, though there will be a high energy consumptions, but you can get it that more safer way, even more purer way and cleaner way. So, there are number of advantages to extracting with carbon dioxide, whether this subcritically or supercritically. Now, one is that no traces of the solvent are left behind versus other methods of extraction using hydrocarbons. So, carbon dioxide is mostly useful solvent at its supercritical conditions, which will give you that non-toxic way of yield of that extraction. Now, again that carbon dioxide is not a volatile solvent, so there is no need for special safety equipment, and also it is a you can say that relatively cheaper, and also it can be recovered and recycled almost 90% of the carbon dioxide which is used in its extraction process. Now, you have to think about that optimization of this supercritical extraction by carbon dioxide gas. In that case, you have to know some strategy for that. What should be that maximizing condition of that extraction process. So, some general strategies are as follows for the optimization of the process, like maximizing diffusion, how it can be done. This can be actually done by increasing the temperature, swelling the matrix, or reducing the particle size. In that case, matrix swelling can sometimes be increased by increasing the pressure of the solvent and by adding modifiers to the solvent. So, some polymers and elastomers in particular are swelled dramatically by carbon dioxide with diffusion, which is being increased by several orders of magnitude in some cases. So, that is why you can maximize that diffusion based on this aspect of this swelling effect, and also the particle size effect, and also that increase or decrease of the temperature there. You can also maximize the solubility. Generally, high pressure will increase that solubility, and at pressure well above the critical pressure, solubility is likely to increase with temperature, and addition of low levels of modifiers such as methanol and ethanol can also significantly increase the solubility, particularly of more polar compounds. So, in that case you have to consider those things, that how to increase that solvation power, and also how that temperature will affect on that solvation power at its critical condition. So, effect of temperature is less as close to the critical point, that actually increase in the temperature causes a decrease in density, and hence the dissolving power there. And you can also design that system based on the optimization of the flow rate there. To maximize that rate of extraction, the flow rate should be high enough for the extraction to be completely diffusion limited, where you can say that wasteful of solvent is the main concern. And to minimize that amount of solvent used, the extraction should be completely solubility limited, but very long residence time there. It is one important shortcomings, but flow rate must therefore be determined depending on the competing factors of that time, solvent costs, capital cost of the pumps, heaters, and heat exchangers. So, the optimum flow rate will probably be the somewhere in the region where both solubility and a diffusion are significant factors. So, these are the factors that you have to consider during your that design of that system, and also case to case you have to take care of those optimizing condition to get that better yield of the extraction process at its intensification way. So, we have discussed several aspects of that supercritical extraction, how it can be done with carbon dioxide to make it solvent and then extraction, and then how it will be that separating, and what will be the general schematic of that supercritical extraction that we have discussed, and how it can be. So, this is one of the important aspect of process intensification in extraction. So, I would suggest you to go further about the process intensification in extraction through these references, and we will discuss more about the process intensification in the successive lectures with other modules like membrane technology, how it can be used in the chemical engineering process as a process intensification. So, thank you for giving attention for this lecture.